So for this video, we'll be solving some examples on our topic work, energy, and power for us to better understand what we have discussed in the concept video. So we have example number 1. So a horizontal force 30 newtons is applied to a 10 newton block on horizontal plane. A frictional force of 25 newtons opposes the motion of the block. If the block travels 10 meters along the horizontal, determine A, the work done by each force, and B, the total work done on the block. So for this, we have here a simple diagram of our problem. So we have here the block, wherein a force 30 newtons is applied to it. Okay, so there is a displacement given at 10 meters. So the force 30 newtons causes a displacement of 10 meters. And also given is a frictional force that would oppose the motion equal to 25 newtons. So to solve now for our work done, we have to identify all the forces acting on the body. So we have the first one, your weight, which is directed downwards. So you also have your normal force. So there are no other forces acting on it, so we only have 4. So the applied force, the frictional force, and our weight and normal force. Okay? So for our solution, so for letter A, work done is equal to force times distance. So we start off first with the work done by the applied force. Okay? So there are angles between our forces and our displacement. So let's use the other equation. Work is equal to force cosine of theta times d. So work now done by the applied force is equal to 30. So cosine of 0, that's the same as 1, times 10 meters. So the displacement is the same as the direction of the force applied. So we'll have a positive work equal to 300 joules. Okay? So next, we solve for the work done by the weight. So for this, the work done by the weight is 10 cosine of 90 times 10, which is equal to 0. So even without solving for this value, we could actually see that the displacement is perpendicular to the weight, wherein we have discussed in the concept video that if the force is perpendicular to the displacement, the work done is equal to 0. Okay? So next, we move on to the work done by the frictional force. So that will be equal to 25 newtons cosine of 180 degrees times 10 meters, or cosine 180 is equal to -1, giving us now a value for the work done by the frictional force as -250 joules. So pag titingnan ko, the direction of the displacement is opposite in the direction of the frictional force, thus it really is a negative value. Okay? And lastly, we have the work done by the normal force. So that is 10 newtons times cosine 90 times 10 meters, which is also equal to 0 joules, since the normal force is also perpendicular to the direction of the displacement. So this is for letter A, the work done by the individual forces. So let's move to letter B. The total work done on the block will simply be equal to the algebraic sum of the work done by the forces. So that is now equal to the work done by the applied force, 300 joules, plus the work done by the weight, 0, plus the work done by the friction, -250 joules, and the work done by the normal force, which is 0. So computing now, the work total is equal to 50 joules. So okay, let's have example number 2. A 40 Newton block is pulled up from rest on a 30-degree inclined plane by a force F equal to 30 newtons parallel to the surface. The motion of the block is opposed by a frictional force of 10 newtons. Calculate for A. Work done by each force. B. The total work done on the block if the block now is pulled for a distance of 15 meters. So for this problem, let's have the simple diagram. So we have here our 40 Newton block. So it is pulled at a distance of 15 meters. Okay. So we have our frictional force. So it's opposite the direction of the displacement. So it was pulled up. So it's directed downwards. So we also have our weight of the block. And we have our normal force. Okay. So for our solution, we'll be using the equation work is equal to force cosine theta times the displacement. So let's start up first with the work done by the applied force F. So in this case, we will have now our equation as work of F is equal to the applied force 30 newtons times cosine theta, which is equal to 0 times the displacement 15 meters. So it's 0 since they are on the same direction. So this will give us now a value of a positive 450 joules. Next, we have the work done by the weight. So as we can see from the diagram, the displacement now, or the line of action of the displacement, is not perpendicular to our weight, as in example number 1. So we cannot say that the work done by the weight is equal to 0. So in that case, I will now be extending the line of action of the weight here, and I'll be measuring the angle between the line of action of displacement and the line of action of our weight, and that is now equal to 120 degrees. So our equation now will be 40 newtons cosine of 120 times 15, giving us a value of negative 300 joules. Okay, so next we have the work done by the frictional force. So we'll have the frictional force as 10 newtons. So that is cosine 180 times 15. So 180 since the direction between the line of action of our displacement and the line of action of the frictional force is in the opposite direction. So the frictional force, or the work of the frictional force, is now computed as negative 150 joules. And lastly, we have the work done by the normal force. So as we can see, the normal force is perpendicular to the line of action of the displacement. So therefore, we have now normal force, which is 10 newtons, cosine of 90 degrees times 15, which is equal to 0 joules. Okay, so we have computed now for the individual work done by each force. So let's move to the second question. What is the total work done on the block? So this is simply the summation or algebraic sum of our individual forces. So that is equal now to 450 minus 300 minus 150 plus 0, giving us a total answer of 0 joules. So as you can see, when there is a force applied and there's an equivalent displacement in our interaction, it is not necessary that we have a value for the total work done. So it's possible that we have here a total 0 work. But for our individual forces, they will have their own values. Okay? So let's move to the next problem. Let's have example number 3. Suppose a spring has a constant of K equal to 500 Newton per meter. Determine the work done in stretching the spring by 2 meters. How much force was required to do the work? So let's have this diagram. So again, if the spring is compressed, then the force applied on the spring is a negative K times X. If we are stretching, or yes, if we are stretching our spring, then that will be a positive X, KX. Okay? So with that, we now are given the spring constant, which is 50 Newton per meter. We're also given your X, which is 2 meters. So you're required to solve for the work done by the spring and the force required to do the work. So we'll just simply substitute the values of K and X in our equations. So for our solution for the work, as we have said, spring is equal to 1/2 Kx squared. And that's now equal to 1/2 times 500 Newton per meter times 2 meter squared. So the work done by the spring is equal to 1,000 joule. Okay? So direct substitution lang yung example number 3. And then for the force, that's simply equal to K times X. So that is equal now to 500 Newton per meter times 2 meters, or F now is equal to 1,000 Newton. Okay? So nagkataon lang na pareho yung magnitude ng work done sa kanang force applied. But it is not always the case. Again, spring work is 1/2 Kx squared, and the force of a spring is K times X. So let's solve example number 4. An object with mass 40 kilograms is placed on the top of a hill with height 100 meters. What is the potential energy gained by the object? So for this problem, we want to solve for the gain potential. So ibig sabihin, if there is a gain, there should be a change in potential energy. Okay? So for this problem, we are given the mass of the object at 40 kilograms. The height of the hill to be traveled is 100 meters. So our required is our potential gain. So for our initial and final potential energies, we'll be solving it using the equation mass times g times height. Okay? So for our solution, we are solving for the gain. So that's equal to mg final minus mg initial, or that's simply mg times the delta h. So substituting all of our given, we'll have the gained potential is equal to 40 times 9.81 times 100 minus 0. So we're assuming that the object was from the bottom of the hill moving to the top. And it is a gained energy, so therefore it should be moving up, or the change in the height should be a positive delta. Okay? So computing, we'll now have a value of the gain potential energy as 39,240 joules, or that's also equivalent to 39.24 kilojoules. Okay? Let's move to example number 5. We have a 75 kilogram man walks on the 3rd floor of a building. What is the potential energy of the man when he goes down to the ground floor? Next question. What would be the man's potential energy when he climbs to the 5th floor? So we would now express our answers for the potential energy in reference of the 3rd floor. Okay? So as I have said, for potential energies, since it is in terms of position or displacement, there should always be a reference. So in this problem, it is the 3rd floor. So for our computations, we'll now use that for every floor level, the height difference is equal to 3 meters. Okay? So for our solution, we'll now use the equation PE is equal to mg times h. So let's solve for the first question. When the man goes down 3 floors from the 3rd floor, So meaning from third floor to the first floor, or from the 3 to 0. So we'll have a height of 9 meters. So 3 floors times 3 meters per floor is 9 meters. Okay? So with that, we substitute mg and then the h. So we have PE now is equal to 75 times 9.81 times 9. So this will give us a value of 6,615 joules. So take note, we are moving down. So it means from a higher position to a lower position. Therefore, our potential energy now is a negative value. Why negative? Since we are below our reference line, which is your third floor. Next, we have next question. When the man goes down 2 floors, so 2 floors, so we'll have a height difference of 6 meters. So we'll use the same equation. We'll just change the value of h. In this manner, we'll have now 75 times 9.81 times 6, giving us a value of 4,410 joules. So for this potential energy, when the man goes up, now his potential energy is a positive value, meaning the man has gained a potential energy. Okay? So again, to clarify, when we are talking about potential energy, okay, gravitational potential energy, when we are moving from higher to lower position, we are having a negative change in potential energy. So we are losing potential energy. But if we are moving upwards, then our potential energy is increased, meaning we are gaining potential energy. That's why we have a positive delta, or a positive change in position, or change in potential energy. Unlike if we have work, if we're talking about work, if we are moving downwards, the work done will by the gravity will be positive, okay? And the work done when we are moving upwards by the gravity is negative. Okay? So, pag potential energy, pag pababa, the change is negative, pero ang work ng weight is positive. Dito, ang potential energy, change in potential energy, pag pataas is positive, pero ang work ng gravity pag pataas is negative. Okay? So next example, we have number 6. What is now the kinetic energy of a 150 kilogram object moving at a speed of 15 meters per second? So in this problem, we are given the mass of the object, 150 kilograms, the speed at 15 meters per second. So we are asked for the kinetic energy, and we know that kinetic energy is equal to 1/2 mv squared. So from the given, we will just simply substitute our values in the equation. So the kinetic energy of the object will be 1/2 times the mass 150 kilograms times the velocity 15 meters per second quantity squared. Or our value now for the kinetic energy of the object is 16,875 joules, or 16.875 kilojoules. Okay? Next, we have number 7. An 8 kilogram block is moving at 3.2 meters per second. A net force of 10 newtons is constantly applied to the object until it has moved a distance of 16 meters. Determine the approximate final velocity of the block. So in this problem, we are given the mass of the object and its velocity. Okay? So therefore, we could apply our kinetic energy. Aside from that, we are also given our net force and a distance or a displacement. So there is work done from the force and the displacement, and there is an energy from our mass and velocity. So in solving problem number 7, we are now going to use our work kinetic energy theorem, which states that the net work of an object is equal to the change in kinetic energy of the object. So as we know, work now is equal to force times distance, and that's equal to 160 joules. And this 160 joules now is equal to our change in kinetic energy, which is now 1/2 mvf squared minus 1/2 vi squared. So from this problem, we know the value of m, and we know that it is initially moving at 3.2 meters per second. So just substitute the values so we can solve for the final velocity. Or we could write this now as 160 joules is the same as Newton meter, and that's equal to 1/2 times the mass, 8 kilograms. So times the quantity, Vf squared minus 3.2 squared, giving us a value of Vf equal to 7.09 meters per second. So it means that the net force 10 newtons will cause a final velocity of 7.09 meters pag 16 meters lang ang kanyang na-travel. Magbabago ulit yung final velocity natin pag nag-iba yung displacement ng object ninyo that is caused by the force. Same goes, the final velocity will also change if we will change the value of your net force applied on the object. Okay? So let's solve problem number 8. A spring of a spring gun is compressed a distance 10 centimeters from its relaxed state. The spring constant of the spring is given at 100 newtons per meter. If a ball of mass 10 grams is placed in the barrel, at what speed will the ball leave the barrel once the gun is fired? So for this problem, for our solution, for here, we are going to use now our spring equations since we are talking about a spring. And also, we have to use our work kinetic energy theorem since there is already a movement of our object, which is your 10 gram mass. Okay, so we'll be applying the work kinetic energy theorem and the work done by a spring. So since we're talking about kinetic energy theorem, so we'll have initial and final values. So we start off first with our initial values. So for the initial spring, that is now equal to 1/2 kx squared. Okay, so it was initially compressed. Okay, so for our initial ke, we have 1/2 mv squared. So since there is no velocity yet in the start, our initial ke will be equivalent to 0. So applying our mechanical energy, our total energy now, initial, is simply equal to the initial spring energy or your potential elastic energy. Okay, so let's move to our final values. So we have our final potential energy of the spring, and that is 1/2 kx squared. But since the spring now goes back to its relaxed position, so therefore our final spring potential energy is equal to 0. Okay, and for our final kinetic energy, which is 1/2 mv squared, okay, so we'll have here the value of the object once it was fired. So applying again our mechanical energy, so initial plus final, or initial that is potential plus kinetic. Since potential is 0, our final total energy now is equal to 1/2 mv squared. Okay, so in that case, we now apply our law of conservation of energy, initial total energy is equal to final total energy. So substituting, we have here your initial, which is 1/2 kx squared, and we have here our final, which is 1/2 mv squared. So substituting our values now, k is 100, x is 0.1, and we have our mass, which is 0.1 kilograms. So we only have one unknown, thus we can solve for the velocity or the speed of the ball after the barrel or the gun has been fired. So V now is equal to 10 meters per second. So let's solve example problem number 9. A 1,000 kilogram car accelerates from 50 meters per second to 75 meters per second in just 20 seconds. So for this problem, we are to determine how much power is required. So for our solution, we'll now be using our equation of power, which is work divided by the time. Or this could also be in terms of energy divided by the time. So for this, we'll now be using the change in kinetic energy as there is a given acceleration. So we'll have delta 1/2 mv squared. So this change in kinetic energy is the value that we are going to use in our equation of power. Okay? So for our kinetic energy, that is now 1/2 times the mass of the car times the change in velocities, so that is final 75 minus its initial velocity 50 divided by the overall time that it changes its velocity. So we'll have here a value now of 78,125 joules per second, or joules per second is equivalent to watts. Converting it now, we could have this as 78.125 kilowatts. Okay? And then, for our last example, we have problem number 10. Who is more powerful? If Iron Man would take 2 seconds to lift a 150 kilogram barbell for a distance of 20 centimeters, while Aquaman takes 3 seconds to lift 300 kilogram barbell for a distance of 15 centimeters. So, in this problem, for our solution, we'll now be using same equation, work over time, but we'll be expanding work as force times the displacement. Okay? So for Iron Man, substitute the values of force, distance, and time. So we'll have 150, that's kilograms. So para maging force, we have to multiply it by 9.81. We have the displacement at 0.2 meters, and the seconds or time is 2 seconds. So the power of Iron Man in his action is equal to 147 joules per second. Okay? And then, for Aquaman, substitute the values of force, distance, and time in the equation. We'll have 300 times 9.81 times 0.15 divided by 3 seconds, which will give us 147 joules per second. So they have the same values, therefore, both Iron Man and Aquaman have the same power. Okay? So before I end my discussion, please do take note that for kilowatts, this is only used if we are talking about electrical energy or mechanical energies. Okay? So motors, okay, or electrical tools. But if we're talking about persons, objects, we indicate our unit as joules per seconds. Okay? So that's it for our examples for work, energy, and power. Thank you for listening.